Today we're talking about planes in three-dimensional. So in my little picture here, this box has 6 sides, so that's like 6 planes. And how would I describe each plane? And that's kind of what we're going for here. So what should I start with? Actually, maybe I should start with a two-dimensional image here. Do you guys remember like what this line is called? XY coordinate plane. Like what's the equation for this line? X equals 3. So because all the x values, all vertical lines the equation looks like that because all the x values on it are 3. So this would be like y equals -2. So a line is to a two-dimensional image what a plane is to a three-dimensional image, basically. So I don't know, what should we start with? Maybe this front plane right here. So based on the fact that this point is at 3, 5, 6, that's messed up. The picture's screwed up over here. Should look more like that. Whatever. Okay. This 3 tells me the x-axis, so that's how far out it's supposed to be. So this plane that's on the front of the box is going through x equals 3, and all the points on the plane have a value of 3. So this plane on the front of the box would just be called x equals 3. Like this point is at 3, 0, 0. This point is at 3, 0, 6. This point is at 3, 5, 0. This point's at, I'm using these numbers to help me figure it out. 3, 5. Anyway, all the points on this plane, what they have in common is an x value of 3. How about, I don't know, the top plane up here. So it's kind of like a horizontal, and it's cutting through the z-axis at, based on this, 6, x, y, z. So it would just be called z equals 6. And technically planes go forever, right? They go off this direction, off that direction. So anyway, the top plane would be called z equals 6. All the points on that plane would have a z value of 6. And maybe this right side over here, it's cutting through the y-axis at 5, so it would just be called y equals 5. Okay, well let's talk about the other 3 planes. Like the left side of this box. What would that be called? Well, if this is called y equals 5, then this one is y equals 0. You guys get it? It's cutting through. So it's kind of like, this is x equals 3. This is, on the y-axis, it's x equals 0. And that's kind of what's happening here. So if this is y equals 5 over here, on the left, it's y equals 0. Okay, if this front plane is x equals 3, the plane in the back is x equals 0. And let's see what I missed, the bottom plane. So if the top plane is z equals 6, then the one underneath is z equals 0. I'll label that, but on the bottom. All so there's kind of a pattern. The planes that are coming out directly at us are all y equals. The planes that are horizontal are z equals, and the vertical planes are x equal planes. Well, and the values kind of match this point right here, because this point is 3 out, 5 to the right, 6 out. So this plane is 3 out, this plane is 5 to the right, this plane is 6 out. Okay. That doesn't really help us with number. We'll need that for later. Doesn't really help us with number 1 though. But graph paper is not really good for 3-dimensional, so we'll just have to sketch this. You guys ready? So make your corner. Two x plus 3y plus 16. Okay, looks like we're gonna have to go out to 6 at the most, so let's make our axes at least 6 long. Let me look at the other ones. 5, 6, yeah, it looks like 6 is as much as we'll have to do. Okay, so our game plan here, let me switch colors, is we're gonna find the intercepts. So let me go back to 2D for a second. If I had 2x plus 3y equals 12, how do I find the x and y intercept? Do you guys remember? Yeah, if I put in like 0 for x, then y would be 4. So, because 3 times 4 equals 12. So 0, 4, that would be the y-intercept. So you just make the x value 0. If I put in 0 for y, I get 2x equals 12. X would be 6. So it would be like out here. So then you connect the dots, and that would be the line. So to find the x-intercept, you make the y value 0. To find the y-intercept, you make the x value 0. Because all y-intercepts, anything on this y-axis, has an x value of 0. All x-intercepts, anything on the x-axis, has a y value of 0. So our game plan for our graph is going to be to find the intercepts. So how do I find the x-intercept? I'm going to make these two at y and z 0. So I would get, if these are 0, I get 2x equals 12. And if 2x equals 12, what does x equal in that case? 6. So I have a point, at 6, 0, 0, which, remember the x-axis is first, so that would be 6, 0, 0. Okay, and then same thing with the y value. I'm going to make the x and z 0, so I would get 3y equals 12. So 12 divided by 3 is 4. So if x is 0 and z is 0, the y value is 4. So 0, 4, 0, which on the graph would be right there. And then for the z, 0, 0, 2. Right, so 0, 0, 2, and that would be right there, 0, 0, 2. And then, well, how are we going to draw this? It'll probably look better on you guys than mine because you can kind of lightly shade with a pencil. I don't really have a function for that on the smartboard, but just connect those dots and you can kind of visualize a plane there, right? Now planes are infinite, but we can't draw infinite things, so, oh boy. And then just kind of lightly shade that in with your pencil. imagination and kind of see the plane. I guess we'll go back. So that's the trick for the first section. Start over. I think the biggest number we'll need on each of these is 6, so just make them all. I'll go to 6 and you should be good. Number 3, 5x minus 2y plus 2z. Alright, so what x value will make, so y and z become 0, what x value will make 5x equal 10? That'd be a 2, so we got a 2, 0, 0. If x and z are 0, well, negative 2y equals 10, so we would need y to be negative 5. And if x and y are 0, 2z equals 10, we would need z to be 5, positive 5. 2, 0, 0, right there. 0, oh, negative 5. Threw me a curveball, I didn't think they were going to do negatives. I think, alright, it's not that big a deal though. You can still do it. So anyway, we need a negative y-axis. I don't think we need a negative z or x-axis here. Go back to red. So that would be 0, negative 5, 0. And 0, 0, 5 would be right here. So there it is. What a beauty, Eva. Just like with an xy coordinate plane, every point inside of our graph here is a solution for that equation. Every like random little point, decimals, fractions, whatever, on this plane is a solution for that equation. Not just the points that we graphed. Okay. Back to blue. Let's try a darker shade. See what that looks like. Number 5. It's a very masculine blue. Does that need to go out to 6? No, it's just equals 2. Okay. You don't really need these at all, actually, but. So 5 and 6 are kind of weird. Do you guys know what z equals 2 would look like? Kind of talked about this at the beginning. Well, you go up to 2 on the z-axis, so it's right there. It's just like a horizontal plane. 2 equals 2. How are we going to draw that? With difficulty. Cheat and use the book here. trick they used. They kind of erased this part. So it looks like the plane is covering it. But they kept that part because it looks like it's punching through the plane. X equals 2. You guys get it? I can still shaded it. If you look on your book, in your books at the top of 453, they kind of show one of each. So, it's kind of helpful. So on 6, y equals 4, you can kind of reference the top of page 453. Help you figure out what that looks like, how you can draw it. Actually, did they draw it? No, they drew y equals 3. Okay, number 6, that's kind of the box, or 7, that's kind of the box I was trying to draw at the beginning. It says that E, that point in the corner is at 4, 6, 1. Let me go back to my original drawing. Get rid of this stuff. So 4, 6, 1 is the point. And the question is, let E 4, 6, 1 be a vertex of the rectangular box shape. Find a Cartesian equation of each plane. So it's kind of this is what I was doing at the beginning. 7a says plane DEFG. Which plane is DEFG? Looks like it's on the top, right? So that would be this one right here. So this top plane is going through the z-axis. So it's going to be a z equals plane. And what is z equal to? Well, based on this tells me that it's 1 up. So it's just z equals 1 for 7a. And then B says plane ABED, which is the front. Okay, the front is cutting through the x-axis at 4. So this plane on the front is x equals 4. For C, it says plane BCFE. BCFE is on the right. And this one's cutting through the y-axis. Where is it cutting through at? 6. So it's just going to be y equals 6. And plane OADG. OADG. Alright, so, yeah, that's one of the weird ones. My jump. So, OADG is cutting, well, it's basically kind of going the same direction as this one, right? So it's a y equals 1, but since here's the y-axis, right? So it's right in the middle of the y-axis, so it's just y equals 0 for that one. Grades, the repeat. Number 9, find a vector. Okay, this is new. This is actually pretty easy though. plus 4y plus 6 equals 12. Okay, so the question in the direction says, find a vector perpendicular to the plane whose equation is given. Now this turns out to be kind of easy. A perpendicular vector would look like, it's kind of hard to draw, but you know, it would be sticking 90 degrees out of the plane, like at a 90-degree angle. So, but all it is, if it's just written like this in normal standard form, the vector is just going to be going 3, 4, 6. Not sure why it works, it just does. That's it, that's all they wanted. Number 11 just says x plus y equals 4. So what do you think that vector, perpendicular vector, is going to look like? So notice I just used what? The coefficients for x, y, and z, right? So what's the coefficient for x here? 1. What's the coefficient for y? 1. What's the coefficient for z? 0. Okay, there's 0 z in there. No z, so just 1, 1, 0. Z equals 1. Kind of the same thing, but much smaller. So z equals 1 is just like a horizontal plane at 1. So what would its vector be? What's the x coefficient? 0, y coefficient, z coefficient. 0, 0, 1. Now if you think about the graph, it kind of makes sense because that's the 1. So 0, 0, 0, 1 would just be going straight up. So it would definitely be a 90-degree angle. Okay. Anyways, number 15. Find a Cartesian vector 2, 3, 6. So it's kind of the same thing as what we're doing, just opposite. So they're starting with the vector, and we're supposed to write the equation that goes with it. So the vector is 2, 3, 5. The other thing that they give us is the plane contains a 3, 1, 7. So this point is supposed to be on the plane. Okay, so basically 2, 3, and 5, the vector that's perpendicular, this tells us the coefficients for x, y, and z. So it's 2x plus 3y plus 5z equals blank. Well, how do I know what it's supposed to equal? Well, that's what they gave us this other point for. 317 is supposed to be on the plane, which means it's supposed to be a solution for the equation of the plane. So if we plug in 317, it could tell us what this value over here is supposed to be. If I plug in 3, 1, 7, and I get 6 plus 3 plus 35, which is 44. Any point on the plane should be a solution to the equation of the plane. I guess it's the last one for today. Number 17. Is it the same thing? Yeah, I think it is. Yeah, it's a little bit weird because the vector is 0, 0, 1. It's kind of like number 13. 0, 0, 1. And the point is 1, 4, 5. Okay, so the x and y coefficients are 0. There is no x and y coefficient. The z coefficient is 1. So it's just 1z, or z equals what? Well, if I plug in 1, 4, and 5, since there's like no x and no y, the 1 and 4 kind of just disappear in the zeros. And the z is 5, so it's just